Welcome back. Today, we're going to build a skill that is, and I mean this, the absolute cornerstone of vector geometry, mastering position vectors. This one concept is the key to describing pretty much any point or path in space, whether you're talking about video game physics or how your GPS works. So, here's our game plan. We're going to start with the absolute basics, then learn the single most important formula you'll need. After that, we'll put it all into practice, working our way up from simple examples all the way to legit exam questions. Okay, first things first, let's lay the groundwork. What in the world is a position vector and why is it so important? It's actually really simple. Think of it like a unique address for a point in space. While a normal vector can float around, a position vector is always locked to a starting point, a fixed origin that we call O. And this image? It shows it perfectly. See that vector, the one we call little a? That is the one and only direct path from our origin, O, to point A. It literally pins A down in space. Everything we're about to do builds on this simple idea. So how do we actually describe these paths with math? Well, we use these standard unit vectors. I for the x direction, j for the y direction, and k for the z direction. So the vector you see there, OP, is just a recipe. Go this far in the x direction, this far in the y, and this far in the z. Simple as that. Okay, so now we know how to get to any point from the origin. But now let's unlock the most powerful tool in the whole toolkit, finding the vector between any 2 points. So this is the big question, right? We've got a path from the origin to A. We've got a path from the origin to B. But what if we want to find the direct route, straight from A to B, without going all the way back to the start? Well, you can think of it like taking a little detour. To get from A to B, what if we first go backwards from A to the origin, that's minus OA, and then go forwards from the origin to B, that's plus OB. If you just rearrange that, you get this beautiful, simple formula right here. Listen, if you only remember one thing from this whole explainer, make it this. To find the vector from A to B, you take the position vector of your destination, B, and subtract the position vector of your start, A. End minus start, always. Got it? All right, enough theory. Let's get our hands dirty and actually use this stuff. We're going to see our end minus start rule work its magic with some classic textbook problems. So here's our first one, right out of the Cambridge textbook. They give us the position vectors for 3 points, A, B, and C. And our job is to figure out the vectors that connect them. We just follow the rule end minus start. For the vector AB, it's going to be vector B minus vector A. Let's do it component by component. For I, we have 4i minus 2i. That's 2i. For j, vector B has 0 j's, so it's 0 minus 5j, which is minus 5j. And for k, be careful, it's 6k minus times negative 3k. That double negative flips to a plus, giving us 9k. And we do the exact same process for AC. It's just C minus A. Now this is the really cool part. Look closely at the 2 vectors we just found. See how AC is just the vector AB multiplied by negative 3? That's a huge clue. It means they're parallel. And since they both start from the same point A, that can only mean one thing. All 3 points, A, B, and C, are on the exact same straight line. Okay, let's step up the difficulty a little bit with a 3D problem. We've got a cube. We need to find the vector that goes from point N, which is the midpoint of one edge, to point P, the center of the top face. Even with the complicated 3D shape, the logic is exactly the same. We want the vector NP, so our formula is OP minus ON. So first let's find the position vector of P. To get there from the origin, we go halfway along X, which is 2i, and all the way up Z, which is 4k. So OP is 2i plus 4k. Now for ON. That's just halfway up the y-axis, so it's 2j. Now we just subtract them. 2i plus 4k minus 2j. And there's our answer. All right, we've crushed the textbook examples. Now let's really put our skills to the test and see if we can apply this core idea to some trickier exercise questions. So this problem gives us a cuboid and asks for 3 different things. This is great because it's going to test our vector formula. Yeah, but also our ability to read a 3D diagram and handle a multi-step problem. And here's the setup. You know, having a clear diagram like this is just everything. It's our map. We can see the origin O, all the dimensions, and the points M and N we need to worry about. Let's break it down. Part A, the height. The problem tells us M is a midpoint, and its K component, its height, is 1. Well, if that's the midpoint, the full height of the cuboid has to be double that. So 2. Easy. Part B, vector ON. We can just trace the path from the origin, all the way along x to 8i, along y to 2j, then up to g, and from there another 4k to get to n. Just add them up. Finally, part C, the unit vector. First, find the vector mn using our rule, on minus om. Then, to make it a unit vector, we just divide that vector by its own length. That gives us a new vector pointing in the same direction but with a length of exactly 1. A classic. A geometry proof using vectors. How can we prove, beyond a shadow of a doubt, that these 4 points make a parallelogram? This is why vectors are so awesome. The proof is so clean. We just calculate the vector for one side, let's say AD. Then we calculate the vector for the opposite side, BC. And look at that, they are identical. That one fact proves they are both parallel and equal in length. We can even double check with the other pair of sides, AB and DC, just to be sure. Okay, it's time for the final boss. Let's put everything we've learned into a pressure cooker and run through a couple of typical exam questions, rapid-fire style. First up, a very common problem. You need to find a point that splits a line segment, but not in half. In this case, we want a point P that's 2/5 of the way from A to B. We use something called the section formula for this, which is just a clever use of position vectors. The section formula is right there on the screen. It looks a bit scary, but it's just a recipe. In our 2 to 3 ratio, you cross multiply. So you take 3 times vector A and add it to 2 times vector B. Then you just divide the whole thing by the sum of the ratio, 2 plus 3, which is 5. Plug and chug, and you get your answer. Next up, an even more common task. Find the midpoint. This is really just a special case of what we just did, where the ratio is 1 to 1. And the formula is super easy. It's just the position vector of A plus the position vector of B, all divided by 2. You're literally just finding the average of the two positions. So for the x components, you do 1 plus 4 divided by 2. For the y components, 2 plus 6 divided by 2. And there's your midpoint. Done. So let's zoom out. What's the big takeaway here? You've just mastered an incredibly powerful tool. By using position vectors to define points and subtraction to find paths between them, you can now describe and solve all sorts of problems in geometry, physics, even engineering. The only question left is, what are you going to solve first?